I'll start with a bit of context, that was for the Rust guys, so it's a bit of what's the safe network, but hopefully now with Spandant's talk I can go fast on this. And then basically I'll cover some of the values of the safe network and how they line up with the Rust programming language. At the meeting for the Rust guys, I complained about the spelling of MadeSafe because I always have to say M-A-I-D safe. Anyway, MadeSafe is the company behind the safe network, and we're building the new internet. That's the tagline. And so the reason we are building a new internet is because we want to reintroduce human values into your online life. So safe network, you guys probably know that, but it means secure access for everyone. And so the idea is to re-give security to everyone without any distinction of if you can afford it or if you're tech savvy and you can protect yourself online. So our core values are privacy, security. So we want to give you a place where you can put your data and you know it won't be lost and it won't be shared with people you don't want to share it with. Then another one of our core values is openness and collaboration. The safe network itself we develop entirely in the open. If you know a bit about licenses, all the backend is GPL v3 with linking exception, and all the front end is BSD MIT. So that means that in the backend, if you want to do a change to the code, you have to contribute it back. But in the front end, if you want to do a change to the code and say do a commercial product, you can do it. So if you want to develop an application on the safe network, you don't have necessarily to give your changes back, although we would like for you to. But if you contribute to the backend, you're required to share your changes. And so the safe network itself, which is all the infrastructure that we're working on, is completely open. But also in the web applications ecosystem, we're encouraging everyone to do it in the open. And then another set of values that are core to our mission is inclusiveness and respect. So secure access for everyone means technology should not discriminate between people based on their level of ability or if they can afford fancy hardware or races or gender or any ground at all. And respect is about giving you respect, like the tools respecting you. If you put your data on, say, Facebook or Google, personally, I feel pretty disrespected. You put your data there and they will mine it and try to make money out of it by selling you ads, taking you for some kind of buying machine, or selling your data to whoever is willing to buy it without any consideration for your privacy or any respect for you. So what we want is to give respect to our users as technology inventors. So that was targeted at people who don't know at all what the safe network is. So I told them, how does it work? It's a decentralized peer-to-peer network that's autonomous, so you don't need human beings to be maintaining it. It's self-sustaining. So we write software that follows a protocol. You run the software and it just works. You don't need to, tweak parameters. Everything is encrypted from the first hop, as we just saw with Spandant's explanation. There are no servers. So this one is not necessarily easy to understand because some people, even if they think of a peer-to-peer network, they think of peers as servers. But we can say very strongly that there are no servers in our model. And one way to define that is that a computer on its own cannot give you a file that you need. Everything is done with consensus amongst a number of computers. So if you're a hacker and you want to access someone's data, never mind the fact that it's encrypted regardless, you cannot just go to a server and get that data, even if you could break encryption. You have to convince enough servers to agree to give you the data. So they're not servers, enough nodes. So yeah, completely serverless. So the overlay network, the routing network, is powered by blockchain-less consensus. I'll go a bit deeper in this in a couple of slides because that's what I'm working on. And the entire thing is lubricated by SafeCoin. So this cryptocurrency, first of all, you can make a cryptocurrency on top of the safe network because when you create a network that gives you the guarantees that your data is never lost and never spied on by people, you can just record transactions as such data, and that gives you the basis for a cryptocurrency. So that's how we can do SafeCoin, and then SafeCoin is used to incentivize you to provide your resources to the network. So for instance, if you run a vault, you're going to be, there is a mechanism called proof of resources that verify that you do give data to users of the network when they request it, and if you behave like this, follow the protocol for a while, you're going to be rewarded in this cryptocurrency. So if you want to know more about the safe network, I'll give you 3 resources. One is safenetwork.tech, or well, the Safe Networks website. There is also a MadeSafe website, but that's not as important. So this kind of will tell you what are our values, a little bit about how it's done. It's a pretty good entry point. There is the safenetworkprimer.com. Some amazing members of the community put that together. So us at MadeSafe didn't generate this, but JPL is one of them. It's a really good explainer for the technology if you don't know anything about it and you want to get an entry point. And right now it's getting a little bit dated, but hopefully update coming soon. I'll remove this soon. Hopefully update coming at some point, no pressure. And then if you want to engage in the conversation, we have an amazing community at the SafeNet forum. For instance, most of you guys actually, and the guys who run the cross test, these kind of guys, they're all from the forum. So if you want to engage in the conversation, just hop in. It's very welcoming. So now I'll just give you a one-liner about PARSEC because that's, so this talk is about the use of Rust in PARSEC, which is the software I've been working on since I joined MadeSafe a bit under a year ago. So PARSEC is something we use in routing to solve a very simple problem, which is you have transactions or say things that happen in the network in a certain order, but because of latency, every member of the network, every node, can see it in different orders. And what you want is to agree on the order in which things happen. That's called consensus. That's called Byzantine fault-tolerant consensus. So the Byzantine fault-tolerant means that some of the nodes can be actually malicious and trying to prevent other nodes from reaching consensus. And so it's a very well-known problem in computer science, and in a way, blockchain is a solution to that problem. But as we've always known since the beginning of the ideas of the safe network, we cannot use blockchain because it wouldn't scale for our use case. So we had to come up with our own. Actually, there are also other consensus algorithms in the wild, but they weren't suited for our needs. And I did a talk actually at this meetup that went deeper into why they aren't suited, etc. So if you're interested, you can find these resources as well. But anyway, so we invented a consensus protocol, and we released the white paper in May. So basically, this is a protocol. It's a piece of maths with proofs that it does what it claims to do. So mathematical proofs. It's equations. It's all based on graphs and how you interpret the graph and deduce an order from the graph that started unordered. And we released the first version of the code in July. And that was code that proves or say that exemplifies that the algorithm works, but that is not yet suitable for use in the actual network for little minor details, such as no node can join the network. So you need to have a fixed set of nodes that will never change. So that's slightly unrealistic. I was for using this only, but Spandan was not okay with it. So yeah, so since then we've been working on making it production ready. So it includes dynamic membership, which is the problem I just described, and also making 100% sure it's rock solid through thorough testing, and also making sure it's easy to access by having good documentation. And so all these things that make code production ready so that you can really trust it. And the code is written in Rust, so if you're not familiar with it, this is Ferris, Rust's mascot. Very friendly crab. So yeah, so
why did they choose a crab for the mascot?
Why did they choose a crab? I don't know, but it's good. He's a friendly crab. Yeah, so it's written in Rust. So actually, all the code in MadeSafe has been written in Rust since the Rust language became stable. And the main reason for that is the Trifecta. So the Trifecta, for Rust people, they already know what I'm speaking about. But basically, Rust's basic promise is to give you speed, security, and concurrency at the same time. That's what they call the Trifecta. So other programming languages, generally you have to choose. For instance, C++ gives you speed because it gives you low-level abstractions. It can give you concurrency because it gives you ways to do that with threads, etc. But it cannot give you security in the way that when you write C++, there isn't really safeguards on you misusing memory. So that means that it's very easy to write C++ code that seems to work, but in production you realize that there is some weird bug, and then these bugs can be exploited to undermine the security of your software. And there are other languages that take a different approach, such as, say, Java, which use garbage collection. So that's something that protects you from misusing memory, but does it when the application is running. And so that means that you pay a performance cost for this. So until Rust, there was really no option for something that's at the same time fast and secure. And especially if you add the concurrency, which is doing things, say, not doing everything in a pipeline one after the other, but being able to do things conceptually on different threads. So when you add that in computer science, that's very complicated, and that even, say, languages like Java cannot resolve this at runtime. So the way Rust gives you this is by being very strict on the programmer at the time your code is compiled. So that means while you're typing your code, tools will tell you you cannot do this because it may be fine, but it may incur a situation that leads to bugs. And so it restricts you more than you could consider strictly necessary, but then the benefit of that is that you can be safe. You know that you will not corrupt memory by construction of your code if it compiles. So yeah, so this, like Rust developers take it for granted. This is why people use Rust. This is why most of the crypto space, say cryptocurrency space projects today use Rust. And actually most of them followed MadeSafe because we were one of the first ones to migrate our code from C++ to Rust.
So it won't compile,
yeah.
even though it will work, but because there's problems with your memory management or security issues, it just won't compile.
Yeah, so you have to write the code in a way that cannot be broken.
How does it detect that? Is it the IDE or?
It's the compiler.
Right.
So I mean, I can give you an example. One rule that is enforced by the compiler is that you cannot have concurrent mutable access to data. So I'll unpack that. Yeah. You've got, in programming, you've got something that's called a variable that's like, you put some state in there. Let's say it represents a word, a string, So it's going to be like hello world, for instance. And so you can say, I'm going to create a string that currently contains hello world, but that is mutable. So later I can change that string. And then in the same function, you can say, okay, change the value of that string to hi world, and then change the value of that string to hi Linux. And so that's two mutable accesses to the same data. And for instance, in C++, you'll have no problem writing that. It's very easy. In Rust, you cannot. So you have to mutate at most once any piece of data. And you see, it's not necessary. The code would work in this example. But what this means is that as soon as you start having concurrency, you cannot have different threads mutating the same data at the same time. So it gives you stronger restrictions than necessary for the simple case, but it gives you safety in all cases, including the complicated cases. Did that?
Yeah, it
help?
makes sense.
Okay.
It's just interesting.
It's a really, like, just for this reason, it's worth picking Rust for any project where security and speed matter.
Does that also make it much more difficult to pick up, you know, for people that...
Actually, I'll come to that, but I don't think so at all, because the compiler is very precise about what in your code is wrong. So it will tell you, you're mutating the same value twice, please don't do this. And so and if you don't understand the one line that it gives you a link to an explanation, then you can go like in the documentation, and it will tell you precisely why you can do this. So it's actually a very good way to learn how to program safely, because the compiler teaches you how to program safely.
Unlike C++, the error messages are clear.
C++ is getting better with Clang and stuff, but yeah. And actually in C++ is trending towards this with static analysis tools. So they try to give you something similar, but Rust is...
It's not built into the compiler, right? It's after,
yeah.
It's after it's compiled.
Yeah. And it's much harder to backport it to C++ because of all the backward compatibility.
Who built and designed Rust, and what was their goal? Was it to replace C++ like systems?
It's sold as or targeted as a systems programming language. I guess who invented it? There is a bunch of people. It's a community. Probably originally Steve Klabnik, Aaron Turon. I'm not sure exactly, so I don't want to. But yeah, it's a number of people. Originally, I think it initiated in Mozilla, and they use it for the backend of Firefox, the current, well, say current and future backend of Firefox. So they used to be 100% in C++, and they care about speed and security. So they invented this language to be able to give you speed and security in the engine behind Firefox. And so they've been working on this engine in parallel with the current engine, but they've been now backporting, or say taking pieces of the code that they've now built into Firefox as they go. So not everything is in Firefox right now, but it's making its way back there. But yes, it's completely developed in the open. Well, I guess now I'm spoiling some of the slides, but it's developed in the open, and they have a process called the RFC process, request for comments. Actually, we stole this, like we are using the same process for accepting suggestions from the community to improve the product, and they do that with the Rust language. So anyway, we picked Rust because of the Trifecta, and that's obvious for Rust programmers. But the point of this talk is to show how there is much more than just the Trifecta, even though on its own it's a good enough argument to use Rust. But there are so many little things that make it really nice to use Rust, and that make it really coincide with our values at MadeSafe. So the first set of values that I'm going to speak about is collaboration and openness. And so I just spoiled you the RFC story. So Rust is developed in the open by the Rust community. And they take contributions from the community to build the language itself. And we use this as well. We took it from them because we thought it's such a nice way to design code. Because currently MadeSafe develops the safe network, but if we're successful, we want for the community to build the safe network. And so we will just be members of the community building the safe network, same as the Rust team. Basically, it's an entire community of enthusiasts about the values of Rust that build it together. This picture was taken this weekend in Rome at the Rust Fest in Rome. I'm here. Yeah, it was very inspirational. If you like these kind of meetings, come to Safe DevCon next year, if that happens.
Where are you going to hold it? Vegas?
Yeah. Are we holding it? Okay.
Yeah.
I'm not sure we're holding it, but if we are, join. Last year was really good. Is it for sure?
We will definitely do something. Yeah.
We'll do something. Join us. It will be like this, but about the safe network. So yeah, another feature of Rust that's really nice for us is that the entire ecosystem, so it's a modern language, it only was made stable in 2015. And from the get-go, they started with tools that allow you to share code with each other, including crates.io. That's a website where all the Rust code that people write gets published if they desire to make it open. And so it means that by default it enables you to get to share code with other programmers in the Rust language. Some other languages have that, mostly modern languages, such as, I don't know, Python, Node.js, these kind of more recent languages. But when you come from an older language like C++, this is a huge win. Because in C++, when you want to, say you want to do something common, you're going to have to find whoever implemented it, and then try to integrate that in your build system. And there are 20 ways to do it, so you're going to have to interface from their way to your way, and it's just a pain. Whereas in Rust, because everyone follows the same standard and the tooling is really good, you can do one command line, cargo add this dependency, and no problem, you depend on it and you can just use it. So that means you don't have to reinvent the wheel all the time. And that's a good example of collaboration. Now, cargo Clippy, okay, no, there is some code. I'll try and explain this in simple terms. But cargo Clippy is a tool that does static analysis. So it means already the compiler is giving you guarantees about safety, but the compiler cannot fail you for something that's valid, because you could be wanting to do something valid. But Clippy, the static analyzer, can detect things that are suboptimal about your code, but that are not strictly an error. So it could be that there is a good reason for doing it, but in general, it's not great. So for instance, in this one, the point is this. This function took an argument that's a Boolean, so that's a yes-no question, and it took it by reference. So that means that it would be put, that means it would give kind of a pointer to this. Okay, I don't know your level in programming. If you don't understand it, doesn't matter. But the point is that the tool tells you, consider passing by value instead. And if you are familiar with it, this can be enough to tell you, okay, I know why. It's because the Boolean fits in 1 bit and the pointer fits in 1 byte, so 8 bits. So I'm wasting resources allocating or like passing a pointer to the thing, which in general is good because a pointer is smaller than most of the data you'd pass. So it would save you passing the actual data. But in this case, because bool is smaller than a pointer, there is no point, so you're just wasting a trivial amount of resources. So it's not that this is a big drama, but it's a little improvement you can make to your code that will have probably no negative side effect, and it just helps you write better code. So this is a succinct description of the problem, but it gives you a link towards trivially copy pass by ref, which gives you a detailed explanation of exactly what's wrong. And so if you don't understand it when you read the one-liner, you can go and get the full description, and then it's really explained clearly so that any programmer can understand this. So you you correct it, and then your code is just that little bit better. And a good thing with this is that you can integrate Cargo Clippy into your continuous integration pipeline. So that means you can run it automatically. Every time you push code, so every time you write code, you can verify that it passes all the Clippy checks, and then that removes all the little paper cuts that you could have. And another nice thing about it is that it teaches you, sometimes when you write things because you don't know a better way to write them, it will teach you little idioms and little better ways to do it. So it's really, really useful. And basically, it's like having the Rust community behind your shoulders, reviewing your code at all time and telling you, hey, you could do this better. Now, another tool that's similar to Clippy is called Cargo Format. And basically, that makes sure that your code is formatted consistently. So, for instance, 4 spaces, then the thing, the scope goes next to the thing and not at the next line. And the point with formatting is that programmers generally have little preferences, but what really matters is consistency. So I'm used to reading code formatted in a certain way. And when I read code from a library I'm using, because everyone uses Cargo format, which has one community decided set of formatting rules. So if you want to contribute a rule, you can just do it. So because everyone uses that, if you read any Rust code in the world, assuming they've formatted it, but everyone does it, you can just read it, and you're not like ticked because there is like 1 space too much here or some little thing. And it seems like nothing if you're not a programmer maybe, but it really saves you mental overhead. Being annoyed at the formatting is a big distraction from what really matters, which is the code. So yeah, Cargo format is a great tool, which again is a way the community collaborates, and that even enables even more collaboration because then everyone can understand each other without having to unpack the syntax. Okay, so the Rust language server is a way that using different text editors, you can access the same resources of the Rust compiler. So you know how you use IDEs, or I guess if you've coded, you've heard of IDEs, programming environments. So these things will give you the power of the compiler while you're writing your code. Anyone, irrespective of the text editor they use, can have access to the best quality tools for writing their code. So basically it turns any text editor into an IDE. Okay, so this was targeted at Rust programmers, so I told them install these tools if you're not using them yet because they're really good. And it's good to be in 2018 because it used to be a more complicated way than this. Now you just type 3 commands and you've got them and they're all in sync. Before you had to use a certain nightly version and it was a bit messy, but it doesn't matter. So now another set of values that Rust and the Rust tooling and the Rust ecosystem helps us with is privacy and security. So I've already explained how the compiler and the part of the compiler that checks you don't do weird things with memory is called the borrow checker. Is a first line of defense against bugs, and it catches the kind of bugs you could have in production for a year in C++ and never notice. And until someone actually exploits it, and then you know, because you lost a lot of money. So that's the first layer of protection, and on its own it's more powerful than practically any language. And then did I mention Clippy before? By the way, Clippy is named after Clippy from Microsoft, so it's not even a joke. So yeah, Clippy, by doing this static analysis, can catch constructs that look iffy. For instance, if you do something like if 0 equals 0, you probably didn't mean that, because why would you compare something to itself? And so Clippy will tell you, don't compare something to itself, and then you can see, oh, I made a mistake, that was a bug. And bugs are the entry point for security problems. So basically the way you hack software is you find bugs and you exploit them, so yeah. So yeah, Clippy is another level of protection. And so with the compiler and Clippy, you get to write code that's very likely to be correct to begin with. But then the problems you can't catch is more complex logical errors. So you thought of the problem in a way that doesn't actually work like you think it does. And so for that, you need to test your code. And I'll show you a few ways we test our code, especially the PARSEC code. So for those of you who've seen the previous talk about PARSEC, you know that we see our problem as these kind of graphs. So it doesn't matter the detail, but these are events and these are communications between nodes. So say these are Alice, Bob, Carol, Dave, and Eric, which are nodes. They communicate to each other and they record it in a graph that looks like this. And when we think of PARSEC, we have images like this in our head. So this graph was generated from a text representation that's called dot. And so this is what it looks like in text form. So you say A0, an arrow, which is minus and greater, A1, an arrow, A2. And if I go back, it gives you A0, A1 relationship, A1, A2 relationship. So basically, this is a way to manually describe relationships. And then because it's such a simple description of a graph, you can easily generate it. So when we run the example or integration tests, we can generate these kind of graphs. And because also it's simple, we can also parse it. So that means you take the graph and construct a graph out, you take the graph. You take the text file, the dot representation of this graph, and you construct a graph representation from it. And to parse it, we're using, of course, a library that's been collaborated by other Rust programmers. So it's another way of collaboration. Okay, so I'm not going to spend too long on this code thing, but what matters is that you parse from the dot file and you can construct a PARSEC instance, which is all representation of this graph, and then you can assert that some invariants you believe should not be violated are indeed maintained. And so this is very convenient if you have an example in your mind of something that could go wrong. So you write the graph, say you can generate it, but say you write it manually, you can visualize it with a picture because you generate the picture from the dot file. And then you express assertions such as, okay, if these nodes communicate to these nodes and this happens, say this node should be aware that this happened, or this node should not be aware that this happened. And so that allows you to describe one scenario and make sure your invariant holds. And that's useful because you can catch problems in your code where you thought it behaved a certain way, but it didn't. But it's not enough because you on your own will not cover all the possible ways to break your code. Because if you could think of them, maybe you'd have coded the code without the bug. So bringing it to the next level is integration testing. And that's where, okay, this seed means that there is some randomness in there. And this schedule with schedule options, it really doesn't matter what it is, but it's a representation of a sequence of events that's sufficiently abstract that you can do you can have the same kind of sequence in many ways. And so for instance here you say Genesis size 2, that means I'm starting with 2 nodes in the network, Pierce to add 8, so that means I'm going to add 8 nodes one by one in any kind of order, it can be any nodes, and then say opaque to add, okay, I'm not going to add any transaction that's opaque, okay, so because this test is adding many peers. So you describe like this the things that you'd like to happen, but you don't describe it as in a specific graph. And because you're passing this seed, you've got some randomness, so you basically can generate any kind of scenarios that satisfy this description. And then you do execute schedule, so you actually run this scenario. Okay, like execute schedule, all this is code So all the work is done in the backend, like in this schedule code. And in this schedule code, we test all the invariants we are aware of. So when we run any of our tests, we benefit from all the invariants. So an invariant is like, I don't know, say, if I'm inputting, if all nodes vote for something, or even if 2/3 of the nodes vote for something, it should be consensus after a certain time. And so you can express these invariants, they're all expressed behind this opaque schedule thing, and then you can describe very concisely a very complex situation in a way that's completely arbitrary, so you can just go randomly and generate all kinds of them. And so you can run this about 10,000, 100,000 times, and you can have good confidence that the invariants you think you're maintaining are indeed maintained in many kinds of situations. And this catches 90+% of our non-completely trivial bugs, where the completely trivial ones get caught even before at the functional test. But we've got something even cooler that's called property testing. Fun fact, I learned about property testing at a Rust meet, at a Rust Fest in Paris. So it's another example of how the Rust community teaches the Rust community how to do best practices. And this thing took us about, I don't know, 2 weeks to code and caught 2 bugs since it exists. So you could think it's not that valuable, but the 2 bugs it caught hadn't been caught by thousands and thousands of iterations of the soak testing that I described before, which makes it extremely valuable because these are the bugs that you don't catch. These are the bugs that you catch after a long time in production. And how does it do that? Well, not only does it use randomness, but you give for any of the ways to build a network, you don't say pick a random number, you don't say pick 2 and then use some randomness to know in which order they are. You say it could be between 4 and 10 peers. It could be between 1 and 10 observations. So you describe a range of possible scenarios. And PropTest, the library we use for property testing, will start by generating an example, like say it takes the middle of every range, for instance, run it, and if it doesn't fail, you tell the framework how to make tests more complex. For instance, if you add more nodes, it's going to be generally more complex. So until it fails, it will increase the complexity of the tests until maximal complexity. And that includes testing edge cases, testing boundary conditions. So in general, in programming, when you get it wrong, it's like when the thing is 0 or when it's very large or these kind of things. And so PropTest will try to exercise all these hard or like places where it's more likely to have bugs. And if it does find a bug, it will then reduce the complexity of the scenario it's generated until it's the smallest it can find that actually breaks the thing. So that means it can go and explore the space of possible things you might have screwed up, like to a degree that even soak testing for tens of thousands of iterations will not cover, because when you go random does not make bad cases more likely. It makes bad cases as likely as good cases. But this thing makes cases that are more likely to trigger bugs more likely to be executed. And so it got 2 bugs for us, and that's a really good result.
Do you need a huge machine or network of machines to run these tests? If you leave it running for a week until it comes up with some answer?
This will run in 10 minutes to an hour on a normal machine. But that's why we specify the range to say be up to 10 peers. If we started specifying up to 100 peers and it tries to make everything complex at the same time, we're going to have problems. Yeah.
What sort of bugs does it tend to find? The really hard ones it knows. Presumably Rust stops most of the memory bugs. So
it's definitely not memory bugs. It's logical bugs. So for instance, we had, in the paper we proved all our assumptions. But then we changed a few things to be more practical to use And in one case, we changed something and we broke one of the proofs from the paper. But in a way that, so what we changed, if you're interested, is that instead of requiring a supermajority, instead of requiring more than 2/3 of nodes voting for something before it reaches consensus, we sometimes allow one node to vote for something and then it reaches consensus. And we know in principle it works because it's just a variant of it, but when we coded it, we broke an assumption we had an assumption, I'm not going to go in details. And we only code this with one of the examples generated by prop test that actually, I don't remember if it stalled, or actually it ran out of RAM and crashed. And because it was just never terminating, so it was continuing to try communicating to each other and never reaching consensus. Last way Rust enables us to have security is, of course, one of the key things in the safe network is encryption. We say everything is end-to-end encrypted. And when you know anything about encryption and security, you know that you should never write your own encryption. So we didn't, but we did write Safe Crypto, which is a library that abstracts away encryption. So for instance, it will say, give me a private key, encrypt a file, give me a public key, sign some data. So these are kind of vocabulary types, these are vocabulary ways to use encryption. And then currently, Safe Crypto really wraps around a very, very old and well-tested encryption library written in C called libsodium. And that's like kind of the industry standard for encryption. Everyone uses it. It's been audited by security experts over, I don't know, decades of usage. So you know you can trust it. But the reason we're using this wrapper is that all libraries depend on this wrapper, and currently there is better encryption libraries that are being written in Rust where you gain the security offered by the compiler. So you can also audit the code and it can also become used into production and really trusted, but then you also can trust in addition of that the compiler gives you guarantees. So we want to migrate in the future to these libraries, but not yet because they're still a few years old, and in security you want for something to have been tested for maybe 10 years and reviewed by a big number of security experts that are going to look for every possible bug before you can really trust it. So currently we're using something that's in C, which because it's in C, we have a bit less trust in it, but because it's been used for decades and vetted and reviewed, we have more trust in it. But in the future, when we have the same kind of confidence in the Rust version, we can just change this library and the entire safe network is now on modern, best-in-class encryption. So that's it for privacy security angle of this talk. And now we can move on to the inclusiveness/respect. And in this section, basically, I'll kind of show how we really share these values with Rust. And in fact, I've got a feeling in modern years, these values are becoming more and more ubiquitous, at least in some circles of the internet. So the Rust code of conduct starts with this bullet point, which says, we are committed to providing a friendly, safe, and welcoming environment for all, regardless of gender, identity of expression, level of experience, which is interesting. But basically, it's for everyone to share in the goodness and no discrimination. And it's not just a line in the code of conduct. If you go on the Rust subreddit or on these kind of places and start slandering people or behaving like this, you'll be banned in no time, because there is a code of conduct and we stick to it. So it's really a cultural thing. Everyone in the Rust community adheres by this value. And that's actually one reason that proportionally compared to other languages, there is much more LGBT representation, much more, say, trans representation, people from minorities, because there is an explicit statement, you are going to be welcome regardless of any of your preferences or such. So this is something, of course, we subscribe to at MadeSafe because we're building secure access for everyone. And so the for everyone means this, basically. Now, in terms of respect and inclusiveness, the Rust language itself, that's something I believe respects the programmer. And in the code of conduct, they say regardless of level of experience, which means you can't shame someone for not knowing something. You educate them if you have to, but not in a condescending way. And this starts with the compiler that gives you error messages that are as precise as you could conceive. And if they're not as precise enough for you, you're very welcome to collaborate and improve it. And that's why they're so good, is because the entire community keeps making it really as clear as possible for uneducated programmers. And so when I'm saying Rust respects the programmer, I'm contrasting it to other languages that try to hide the complexity from you. And that's a way that they try to respect the unexperienced programmer by not putting them in hard situations. But the problem with this is that this hinders expert programmers from getting the performance or the behavior they want because they've been hidden too much to actually get what they want. So Rust at the same time respects the new programmer by teaching them programming, but also it helps the expert programmer by letting them do what they want to do. So there are things that it prevents you to do, for instance, mutating the same data twice, but on another hand, it gives you access to low-level abstractions, which means you can actually do anything that you need for getting speed in your program. Also, did I mention Clippy? So Clippy, I think, is also a way to be inclusive, because as I was saying earlier, it's like someone is reviewing your code all the time, someone who's got much more combined experience than you, and they teach you, even though it's a tool, but like it teaches you how to write code in an idiomatic fashion. And so I think that's a very, very good way to be inclusive to new users, because they can immediately get up to date with the current modern way to write the language with this tool. And so this was about Rust respecting the programmer, but for instance, most of you guys probably are not programmers. And another aspect of it is that Rust respects the user. And here I'm just going back to the trifecta that I quoted before of safety, performance, and concurrency. Today, where our life is on our computers, I believe that at the very least safety, so your data, what you're doing not being exploited by hackers, is practically a human right. And performance, I also consider very, very important, because not writing performant code is discriminating between people who can afford expensive hardware and people who can't. And so I believe that performance is absolutely critical as well in terms of 2018 human rights, digital human rights kind of thing. And then another way Rust is very good at being inclusive with the community is the documentation ethics. One, the tooling makes it very easy to write documentation. Two, it's in the culture that everyone who writes Rust code tries very hard to write comprehensive documentation. And that's another way that the entire community collaborates. And if someone uses a library and it's not well documented, they're quite likely in the culture of the Rust community to contribute an improvement to the documentation. And at MadeSafe, we're trying very hard to follow in the footsteps of the Rust community for this. And so all our code that we write in Rust that we share with the community, we document as much as we can. And that's a hard thing to do. It takes a lot of resources. It's not easy to explain your code simply, but it's something that we see almost as a duty to the wider community. Because if you just write code and publish it and say, oh, but you can just be smart and read the code and you'll figure it out, that's not inclusive, that's not respecting the community members you're interacting with. And finally, performance. As I said in the human rights thing, performance is a way that you can include people who can't afford good hardware. So in the safe network, like, we want to gain maximum performance we can. And we want for it to be ubiquitous to use on any hardware that people would realistically have, like your grandmother's laptop, which is 10 years old. Now, a little anecdote about performance. I guess if you read the dev updates, you may have seen this picture. These are Flamegraphs. They're a way to visualize the performance characteristics of your program. It's not something created by Rust. It's a tool that works for C++ or other languages, but it's a nice tool to troubleshoot performance. So basically, you can have a visual representation like this of what's slow in your code. For instance, here, I don't even know what this is about. I see this is fat. It means in this function, something happens that takes a lot of time. So I go to this function, I check what it does, and I make it faster. And I don't have to look into my entire code to know what's slow. I can see directly what's slow here.
Did you say that's a Rust tool?
It's a general tool that works, for instance, for C++. But you can use it with Rust.
Does it augment your source code? Does it put some stuff in there?
No, because, okay, Rust is, okay, maybe I'm going to lose some of you, but Rust is based on LLVM, which is a compiler and a set of compiler tools that can compile different languages. So for instance, LLVM can compile C++, Objective-C, I think, no, not Java. Well, okay, C++, Objective-C, C, and a few languages. And so all the tooling above that is shared between these languages. And so this is generated with Perf for measuring the performance on Linux, and Flamegraph for representing it in that visual way. And these are standard tools that you can use with C, C++, but that also happen to work in Rust. And so in that case, this was targeted at Rust programmers. So I was telling them, if you haven't used it, go check Brendan Gregg's website. There is tutorials, and that's a really, really good way to fix your performance. Something that any programmer will tell you is to fix performance, first measure. Now, credits to my team, because I just spoke about a ton of cool stuff that we did, and literally everything was done by them. So yeah, thanks for them. And thanks for the Rust community and Made Safe for enabling all this. And thank you guys.
15 minutes before we're supposed to be out of the building, so there's time to ask questions if you haven't.
Since Rust is changing very fast, you know, I think it's first version's 2014, was it, or something? It's very new.
It was stable. I mean, it started in 2008, but it became stable in 2015.
So is everything always backwards compatible, or do you have these sort of charitable version problems?
Everything is backward compatible until, so the point of Rust being stable is that from that point on, they guarantee backward compatibility. But in 2018, to enable bigger enhancements in the language, actually in December this year, they're going to release Rust 2018, which will allow you to break backward compatibility, but you need to pass a flag to the compiler. So it's like, I don't know if you're familiar with C++.
Yeah.
Okay, so it's like C++ 11, 14, 17. You can say compile my code as C++ 17, and then it's going to compile different code, but you can compile it as C++ 14, and it will never break. So some minor things may have been deprecated, but they won't be if you use the flag for the older language. So in this case, basically it means you can always use the latest compiler to compile your oldest code, but you can also use the latest compiler to compile code that's more recent, but then it may break backward compatibility for you, but that's okay.
I can research this on the net afterwards, but I'll ask it because we've got 10 minutes to go. So, alright, calm down, I'll be quick. So in terms of the richness of the language, right, is it statically typed? Does it have lambdas? Can you pass functions to functions, that sort of thing? Or is it quite prescriptive in how you... I know it's prescriptive in compiler errors and stuff, but I'm talking, Node.js allows you to, throw things around.
It's completely statically typed.
Okay.
It encourages a functional programming style. So
it
you
encourages
definitely
functional programming.
Yeah.
Okay.
You definitely have lambdas. You don't have to write functional programming, but it's multi-paradigm.
Yeah.
But I guess the clean way, in my opinion, is to be more in the functional side.
Right.
It's not something like Haskell that's like die hard.
That's the only thing you do, yeah. Right.
This is more like pragmatic functional.